So and then I'm gonna bring up the OBS now. And just a minute. Right here. Just give me a few. So we're gonna look at the FET. So we're bringing up a video for it. Let me just bring up the video.
The following program is brought to you by Element 14.
Let me just bring it up
The
here.
following program is...
And then share now. So I'm gonna share. Alright, so I'm using the OBS to record it. Let me see if I can record it from here. No, we can't do a record privilege. So I'm using the OBS to record. Right. Can everybody see my screen? Hello? Can everybody see my screen?
Yeah.
Alright. So we're gonna talk about the FET now, and the FET field effect transistor, and as the name implies, it uses voltage to turn it on. You see, whereby we have IB for the base, the base current for the BJT. We use the base current to turn it on. We're gonna use voltage to turn on these types of transistors. These type of transistors still have 3 terminals, but instead of base, emitter, and collector, we have gate, drain, and source. The gate is like the base, the drain is like the collector, and the source is like the emitter. Alright, but it works a little bit different. They look similar in package, but the only difference is that once you know the number, the model number, or the number of on the transistor itself, because all transistors have a number, then the specification will tell you whether it is a field effect transistor or a BJT transistor. Alright, so here goes. We're gonna look at a video with element 14.
Brought to you by Element 14, the electronic design community where you can connect and collaborate with top engineers from around the world. Join now at element14.com.
Hi, and welcome back to the Learning Circuit. Today we're going to learn about field effect transistors, or FETs. There are 2 basic types of FETs, the junction field effect transistor, or JFET, and the metal oxide semiconductor field effect transistor, or MOSFET. Previously, we learned about bipolar junction transistors, BJTs. They have a collector, emitter, and base. FETs, instead, have a source, drain, and gate. The source can be compared to the collector, the drain like the emitter, and the gate performs similarly to the base. While BJTs have a linear structure with 2 PN junctions and are either NPN or PNP, JFETs and MOSFETs have PN junctions configured in a way that gives them their unique characteristics and functions. Let's start by looking at JFETs. Here are 2 different visualizations commonly used to represent the inside of a JFET. Notice the different layout of the N-type and P-type regions. One type creates a channel directly connecting the source and drain, while the other type sort of surrounds it and connects to the gate. JFETs are named for which type makes up the channel: P-channel JFETs and N-channel JFETs. The current flowing through the channel can be controlled by varying the voltage at the gate. We'll start with an N-channel JFET. We know from our diodes lesson that connecting a PN junction in reverse bias will cause its depletion region to grow. The depletion region acts as an insulator, restricting the flow of current. By increasing or decreasing the depletion zone at the PN junctions, we can control the flow of current through the channel. As you can see, the source and drain are connected by a single region. When a voltage is applied across them, current flows freely between them as if the two leads were shorted together. The JFET is essentially on by default. Now, if we apply a second voltage across the gate and source terminals, but in reverse bias, a depletion layer will form where the P-type and N-type regions meet. In an N-channel JFET, this requires the gate source voltage to be less than the drain source voltage. The more biased the gate becomes, the more the depletion region grows, the narrower the channel becomes, constricting the flow of current through the channel. The channel can continue to narrow until the current is cut off completely. The voltage difference at this point is known as the cutoff voltage. To increase the bias, the gate source voltage has to be lower than the drain source voltage. To do this, you can either increase the drain source voltage or decrease the gate source voltage. The depletion region grows or shrinks relative to the difference between the voltages. The higher the difference in voltage, the more the depletion region grows, the more current is restricted or decreased. The less the difference in voltage, the smaller the depletion region is, the more current flows. It increases. N-channel JFETs are used far more commonly than P-channel JFETs, but they effectively work the same way, simply with a reverse polarity. In a P-channel JFET, the gate would be connected to positive rather than negative. This also means that the gate...
Alright, let me just stop here to explain something. When you say N channel and P channel, what they are talking about is this right here, so. This inside right here, this is the channel. This is just one piece of substrate that join the drain and the source. So by default, the N channel, this is on totally. Alright? And the only way you cut it off now is to increase the voltage on the P on the P channel on the gate. Same thing right here, so this is a P channel inside here, so this is the channel inside here. And to cut it off, then you would have to increase the voltage again at the gate again. Right? Notice that this P right here so can grow when you put a voltage on it. Both of it does grow, and it's like a pipe, and it does close off whole entire thing. Same thing with this right here, so this P type can grow as well too, and push the end straight across, push the end and push the end out. Right, and cut off whole entire thing, or it can bring it in as well.
Gate source voltage has to be higher relative to the drain source voltage, rather than lower. Okay, we know that the gate has to be reverse biased for the JFET to function, but what happens if we forward bias the gate? Well, sadly, the gate junction is not really designed to handle any significant amount of current, and if current were to flow through the gate in forward bias, it would probably destroy the component. JFETs are known as depletion mode devices since they rely on the growing and shrinking of the depletion zone. But that's not the only way a FET can function. While JFETs are strictly depletion mode devices, MOSFETs can be either depletion mode or enhancement mode devices. The main difference is in their construction. Depletion mode, or DMOSFETs, have a physical channel connecting the source and the drain terminals. In enhancement mode, or EMOSFETs, the source and drain are not connected and rely on the gate voltage to form a channel between them. JFETs are junction field effect transistors, using their PN junctions to affect the fields within the device. MOSFETs have a metal oxide semiconductor. The name comes from the metal conductor of the gate, which connects to a silicon dioxide insulating layer that is between the gate terminal and the semiconductor that makes up the substrate in the rest of the component. The foundation of the MOSFET is called the substrate. N-channel MOSFETs have a P material substrate. P-channel MOSFETs have an N material.
It go really quiet. We are cut off just now. We just cut off like a while. We got a cut off like a while ago. Hello? It cut off?
Yeah, man, yeah, it cut off.
It cut off for long?
Put her with the
No,
stop.
no, no.
Oh, okay.
Just like about a minute.
Oh, oh. So you want me to show about the video then?
Show about the video.
Okay. Like about up here, so.
It above in
JFETs are strictly depletion
so
mode
do you put the
devices.
link in
MOSFETs can be used in
Oh.
depletion mode.
like here side of the internet above
Uh,
so that's the
all right, all right. Let me. I'm gonna put the link in the group. Hmm. I'm gonna put it in the classroom. What FET mean again? What FET mean, people? What does FET mean? It's a field effect transistor. A field effect. FET means field effect transistor.
Or enhancement mode devices. The main difference is in their
So
construction.
it's flex.
Depletion
so the
mode
J
or
is what? The junction
Junction field effect
have a
transistor.
phys-
So the MOSFET is a metallic oxide semiconductor field effect transistor. So the D is for depletion and the E is for enhancement type. Right? So this is depletion metallic oxide semiconductor field effect transistor. This is enhancement type metallic oxide semiconductor field effect transistor.
physical channel connecting the source and the drain terminals. In enhancement mode, or eMOSFETs, the source and drain are not connected and rely on the gate voltage to form a channel between them. JFETs are junction field effect transistors, using their PN junctions to affect the fields within the device. MOSFETs have a metal oxide semiconductor. The name comes from the metal conductor of the gate, which connects to a silicon dioxide insulating layer that is between the gate terminal and the semiconductor that makes up the substrate in the rest of the component. The foundation of the MOSFET is called the substrate. N-channel MOSFETs have a P-material substrate. P-channel MOSFETs have an N-material substrate. The MOS acts like a capacitor. Due to the insulating oxide layer, the conductive layers don't touch, and therefore, current can't flow between the gate and the rest of the FET. But if the metal conductor at the gate becomes charged, it will cause an equal and opposite charge in the semiconductor substrate, just like in a capacitor. Let's look at an N-channel DMOSFET. Like in a JFET, the drain and source are connected by a channel.
Go
No
and watch it. Let me
connection
turn
or
on the
voltage
AC.
at
Go and
gate
watch
is
it.
required for current to flow between the source and
not
the
seeing
drain.
anything without it.
The MOSFET, by default, is effectively on.
So
When there is a voltage at the gate, and the gate is reverse
also-
bias, the DMOSFET is operating in depletion mode. It behaves like a JFET. As the bias of the gate grows stronger, the depletion zone also grows. Proportionally, the channel is narrowed, increasing the resistance and restricting the flow of current through the channel between the source and drain. Now here's where the DMOSFET is different when it operates in enhancement mode. The gate is connected to a voltage in forward bias. Polarity at the gate draws charge carriers from the substrate towards the channel, effectively widening the channel. The channel grows
So-
beyond its
Yeah?
default size.
Not seeing anything on the screen.
You not seeing anything on the screen?
Huh?
Hold on. Oh, it only sharing. Hold on, let me say minute to go be about that, man. Come today, I enjoy it and nothing, so no enjoy it too. Think you're seeing it. Alright, so we're gonna
First
do a from
polarity.
here, so.
In a p-channel JFET, the gate would be connected to positive rather than negative.
So, you see the spot already? You saw the spot already?
No, you can't start it here, sir. You can't start it here, sir.
Okay.
Also means that the gate source voltage has to be higher relative to the drain source voltage, rather than lower. Okay, we know that the gate has to be reverse biased for the JFET to function. But what happens if we forward bias the gate? Well, sadly, the gate junction is not really designed to handle any significant amount of current. And if current were to flow through the gate in forward bias, it would probably destroy the component. JFETs are known as depletion mode devices since they rely on the growing and shrinking of the depletion zone. But that's not the only way a FET can function. While JFETs are strictly depletion mode devices, MOSFETs can be either depletion mode or enhancement mode devices. The main difference is in their construction. Depletion mode, or DMOSFETs, have a physical channel connecting the source and the drain terminals. In enhancement mode, or EMOSFETs, the source and drain are not connected and rely on the gate voltage to form a channel between them. JFETs are junction field effect transistors, using their PN junctions to affect the fields within the device. MOSFETs have a metal oxide semiconductor. The name comes from the metal conductor of the gate, which connects to a silicon dioxide insulating layer that is between the gate terminal and the semiconductor that makes up the substrate in the rest of the component. The foundation of the MOSFET is called the substrate. N-channel MOSFETs have a P material substrate.
Hearing it? Everybody hearing? Hello, everybody hearing it? Everybody hearing it okay?
Yeah, so it's my ear.
Okay.
P-channel MOSFETs have an N-material substrate. The MOS acts like a capacitor. Due to the insulating oxide layer, the conductive layers don't touch, and therefore, current can't flow between the gate and the rest of the FET. But if the metal conductor at the gate becomes charged, it will cause an equal and opposite charge in the semiconductor substrate, just like in a capacitor. Let's look at an N-channel DMOSFET. Like in a JFET, the drain and source are connected by a channel. No connection or voltage at the gate is required for current to flow between the source and drain. The MOSFET, by default, is effectively on. When there is a voltage at the gate, and the gate is reverse bias, the DMOSFET is operating in depletion mode. It behaves like a JFET. As the bias at the gate grows stronger, the depletion zone also grows. Proportionally, the channel is narrowed, increasing the resistance and restricting the flow of current through the channel between the source and drain. Now here's where the DMOSFET is different when it operates in enhancement mode. The gate is connected to a voltage in forward bias. Polarity at the gate draws charge carriers from the substrate towards the channel, effectively widening the channel. The channel grows beyond its default size. This allows more current to flow through the channel than is usually possible. So DMOSFETs can work with zero bias, reverse bias, or forward bias at the gate.
I'm gonna experiment probably about next week. I want to show 2 more videos with it, and then we'll do some experiment with it next week.
DMOSFETs conduct only in enhancement mode. In depletion mode, the reverse bias of the gate narrows the channel, restricting flow. As you can see, there is no channel between the source and drain, so there's nothing that can be narrowed. For current to flow between the source and drain, the MOSFET has to be in enhancement mode in order to create a channel. For the gate of this N-channel eMOSFET to be connected in forward bias, the gate is connected to positive power. The positive gate voltage attracts negative charge carriers, joining the N-type regions of the source and drain, creating a channel between them. The more voltage applied at the gate, the wider the channel gets. If the voltage is lowered back down, the channel will narrow. The minimum amount of voltage required at the gate to create a channel is called the threshold voltage. To summarize, we have JFETs that only work in depletion mode. They are always on unless acted upon by a voltage at the gate, which can decrease the flow of current through its channel. eMOSFETs only work in enhancement mode. They are by default off, requiring a voltage at the gate to create a channel between the source and drain. And DMOSFETs that can work in depletion or enhancement mode. Like JFETs, they are also on by default, but a voltage at the gate can cause it to decrease or increase the current flowing through its channel. There's a lot more information to learn to be able to use FETs effectively in a circuit. Lots of voltage and current math. But hopefully with an understanding of how each FET works, you've got a leg up on learning that next step. If you have any information you'd like to add to today's lesson, or questions you'd like to ask, Please post those on the Element 14 community on element14.com/the learning circuit. Happy learning!
Alright, so we're gonna look at another one now. I'm gonna see we can use our JFET to turn on a simple motor. Let me just find that, bring up that one. It is coming up shortly.
My name is Christine. I live in Jersey City, New Jersey, and I went from working in healthcare to being a software engineer in one.
Hi, I'm James, the Bald Engineer. Both of these are Hi, I'm James.
Mr. Hudson,
Yeah?
it's a 10:30. I have to go around 10:30.
What time is it now? 9:40? We have up time, man. Up time. Alright, so we're gonna do some. I'm gonna show this one now. This one is the. So I'm gonna share this. Alright. So this is how you can use the JFET, and we're gonna get some equation. You're gonna write down these equations because you're gonna use them. And we're gonna do some experiment next week. So we're gonna use the equations to do the experiments. Alright. This one is a little funny. Is that enough funny? When we say funny, is that it is in the full of joke, right? That little person is full of joke, but him bring across it very, very clear. Or you can use a MOSFET or a FET to turn on a motor.
Hi, I'm James, the Bald Engineer. Both of these are transistors. One is a BJT and the other is a MOSFET. Can you?
Alright, which one is the BJT, which one is the MOSFET?
The one to the left for the MOSFET.
The one to the left is MOSFET. What it mark on? 2N or IC4 130N06 cell?
IC4.
The one mark on IC4. Alright, yeah, that more look like a MOSFET. Or you tell the difference?
Me look for the construction now.
Alright, but I answer that question. Alright, let me just stop it a little bit. And share my camera. Ask it to show me. Oh, the camera can't turn on. No, you know why the camera can't turn on? Because it is using something different. But I would have to stop this. I would have to share. Go on a different computer. I'll show it, but it doesn't really make any sense. But if I show you some other transistors, how do you know the difference between a MOSFET and a JFET? Most of the time, you'd have to use the number that is on the transistor itself, right? But sometimes what I use this little funny looking writing here, this little F, to know that is a FET. Most of the time, you see the F on it, on the transistors. Because you have BJT that looking just like this as well. Alright?
Can you tell the difference? If not, that's okay, because in this Adams video, we're going to take a look at MOSFETs, how they work, and how you can use them in your circuits. So let's get going. This video is part of a two-part series on transistors. The previous one covered bipolar junction transistors, BJTs, while this video covers metal oxide semiconductor field effect transistors, known as MOSFETs. Generally, you'll use a BJT for small loads, say less than 1 amp of current, while MOSFETs are well suited for applications with much higher current. For the video on BJTs, see adoms.com/EP10. For now, let's move on to MOSFETs. Moss is a flowerless plant that typically grows 1 to 10 centimeters. Some mosses grow up to 50 centimeters and can be commonly found on trees. Wait a minute. This is the wrong script. Hold on. The tree sounds right. Okay, here's the other stuff. Okay, let's try this again. MOSFETs belong to a family tree of field effect transistors
I tell you, full of joke. I'm gonna talk about moss with the pan tree.
or known as FETs. There are JFETs, MOSFETs, and IGBTs. JFETs actually work a little bit like a BJT, which we've already talked about. For this video, we're focused on the MOSFET, which has two types of modes called depletion and enhancement. A depletion mode MOSFET works like a normally closed switch. Current can flow when no voltage is applied. Applying a negative voltage actually causes the current flow to stop. An enhancement mode FET works like a variable resistor. They come in N-channel and P-channel types. Enhancement mode FETs are by far the most common transistor used today, so let's focus in on them. Here's the symbol for an N-channel, so let's focus in on them.
Alright. So we have different type of transistors. So all of these, everything right here are transistor. The last transistor that we're dealing with is the bipolar, which is the BJT. So we have bipolar, but how many type of bipolar do you know? What are the two common type of bipolar?
NPM and PNP.
NPN and PNP. Alright. So whether it is FET or bipolar, what is the material? What is the material known? What two material that you can use to make any transistors at all, or any semiconductors?
Silicon and germanium.
Silicon and germanium. Alright, and this is a different type of transistor. We're not gonna get into this right now. You're not doing this for the course. If you choose to do the first degree, then we'll deal with this, right? But for now, we're dealing with the bipolar and the FET, all right? But we're mainly gonna deal with the MOSFET for now. But the exam will ask you for JFET as well, all right? So with the FET, you have two types. You have the junction FET and you have the MOSFET. But with the junction type, you have depletion, and it is an N-channel type. With the MOSFET again subdivided into two types: the D type and the E type, which is the depletion and the enhancement. But the depletion type again is only N-channel. But with the enhancement type, it has both N-channel and P-channel MOSFET. So it's P-type and N-type MOSFET. Alright?
Here's the symbol for an N-channel enhancement mode MOSFET. And here's a TO220 style transistor. The pins of a MOSFET are identified as the gate, the drain, and the source.
Take that in good. The gate, the drain, and the source. Notice it's still like a little L right here. And this one is like a little E with the arrow going inside of it.
The field effect part of their name suggests they work by voltage, compared to a BJT, which works by current.
Remember, I told you that before we start. So if you get a question like this, which transistor use voltage to turn it on? What would you? Which group of transistor use voltage to turn it on? What would be your response?
SMS.
Which group of transistor use voltage to turn it on?
Voltage is straight out. The MOSFET one.
The FET. All I FET them. All FET. Whether it is JFET or MOSFET, all FET use voltage to turn it on at the gate. Or to control it. To control the current between the drain and the source. So to control the current between the drain and the source, at the gate have to use a voltage. But for the BJT, to control the current between the emitter and the collector, what do you use at the base to control it? Current. So the BJT use current to control the base, and the FET use voltage to control the base. So the FET is a voltage operated device, while the BJT is a current operated device. You understand that? Alright. So with the out of the FET and the BJT, which one can handle more current?
Which I can more current.
Mm-hmm.
That's the BJT can angle more.
No, the FET can handle more.
So the current can flow through the barrier. The current sometimes.
That's why when you start off, you were saying that let me go back up here again. I'm gonna jump back right down to where I am, but listen this carefully now.
Adam's video, we're going to take a look at MOSFETs, how they work, and how you can use them in your circuits. So let's get going. This video is part of a two-part series on transistors. The previous one covered bipolar junction transistors, BJTs, while this video covers metal oxide semiconductor field effect transistors, known as MOSFETs. Generally, you'll use a BJT for small loads, say less than 1 amp of current, while MOSFETs are well suited for applications with much higher current.
You see that now?
Okay.
You see that? Right. So the MOSFET use more current. So let me go back to here now.
FET. And here's a TO220 style transistor. The pins of a MOSFET are identified as the gate, the drain, and the source. The field effect part of their name suggests they work by voltage, compared to a BJT, which works by current. When voltage is applied between the gate and the source, current is allowed to flow between the drain and the source. Here's the really cool thing about MOSFETs. They are variable resistors controlled by voltage, which means depending on the voltage applied between the gate and source, the resistance between the drain and source will vary. With a low voltage at the gate, the resistance from the drain to source is very high. It's kind of like an open switch. As we increase the voltage at the gate, we pass a threshold voltage, and then the resistance from the drain to the source drops, and it drops very quickly. The key difference between a MOSFET and a BJT is that the
Alright. So the voltage that is used, the voltage that really causes it to turn on, is known as a threshold voltage. You understand? When the voltage is very, very low and there's no voltage, the resistance is very high, or it acts like a open circuit. But once you start to increase the voltage at the gate, you reach to a point where it starts to break down the resistance, and then it reaches to a specific point where it turn it on and the current start to go through. That's known as the threshold voltage. That's the voltage that causes current to start to go through. So once you apply voltage at the gate of a FET, and current start to go through at that specific point, that voltage is known as a threshold voltage.
The output current isn't a multiplier of the input, because MOSFETs are all about voltage. Since the resistance is between the drain and source, it is known as RDS on, and can always be found in the MOSFET's datasheet. For example, this is a FQP30N06L.
Last group, Roger's group, that is Roger, Chasey, Andre, and Giovanni. I let them experiment. Their labs was use these transistors. I went to Africa and I bought these transistors, and I let them conduct this experiment, and I see that it worked. So this was one of their labs for last year.
Let's take a look at its datasheet from Fairchild. We can see that RDS is given when there are two different voltages from gate to source. At 10 volts, the on resistance will be about 27 milliohms. And while at 5 volts, the on resistance is only about 35 milliohms. That's pretty small when you think about it. We picked this MOSFET on purpose. It is known as a logic level MOSFET because the voltage from gate to source VGS is lower than 5 volts.
And not only that, I remember when you made your logic, no, not your logic, but your transistor switch. You made your switch to the transistor, bipolar transistor. They made your switch with this type of transistor, and they connect it to the computer. Can the computer give out a logic level? So they connect it to the parallel port of the computer. We download a software and we use a software to control the voltage that is coming out of the parallel port, and we use the parallel port to turn on devices.
In other words,
Not all FET or MOSFET are logic level. So if you want to control from the computer or from a logic gate, like an AND gate or a NOT gate or a hard gate, from a logic gate that is, then you have to buy a specific type of FET. And this one, the FQP 30N0Q06L, is a logic level one. So this can use on the computer, and it can also use you can use an AND gate. You can use some gate or the other, some logic gate, to power on the gate part of it, right? To turn on the gate. Because the voltage, this voltage right here, that is coming out of the logic gate. You don't even really have to even use any chance in the resistor. The voltage that is coming out of the logic gate is enough to power the gate of the FET.
the threshold to turn the MOSFET on is low enough to be used by an Arduino or Raspberry Pi. Not all MOSFETs are logic level compatible, so it is very important to check to see what the VGS threshold is before using it in your circuit. Since you will probably use a MOSFET in high current applications, it is important to check how hot it is going to get. Here's how we calculate if we need a heatsink or not. The formula to determine how much power the MOSFET dissipates is resistance times current squared. In this case, the resistance is RDS on, and the current is whatever your load will draw. Let's use an example of a motor that draws 1 amp of current. This means we multiply 35 milliohms by 1 amp squared to get 35 milliwatts. Okay, now we need...
Where did they get this 35 millivolts from? From the data sheet.
a few more things from the datasheet. First, we need the junction to ambient coefficient, which is R theta JA, and in this case is 62.5 degrees C per watt. We also need the maximum junction temperature, which in this case is 175 degrees C. Using this formula, we can calculate the maximum power the transistor can dissipate without using a heatsink. We take the maximum junction temperature minus the ambient temperature, which is going to be 25 degrees C, and divide by the thermal resistance.
When I talk about ambient temperature, is room temperature, 25 degrees Celsius. Right? So they get this for the data sheet, the 175 degrees Celsius, and they get the 62.5 from the data sheet as well, multiplication from the data sheet. So you get this for the data sheet, and this is room temperature.
This gives a maximum dissipation of 2.4 watts. In our example, we are only dissipating 35 milliwatts, so we're safe to operate without a heatsink.
Everybody understand that? Everybody understand the concept? Everybody understand that concept?
Yeah, I understand what them do. Them just get the information I get it from the data sheet. I just know said minus the from the ambience temperature, and then they go have 150 Celsius over 62.5 kilo Celsius watts. So you know, say 2 Celsius cancel. So left it now watt.
Yeah.
Put in out
Yes.
2.5 watts.
So what about this 25? Where does 25 come from?
And the 25 come from the data sheet.
All right. And look at this again now. Let me show you something different. All right. So the RDS on, they come from the data sheet as well.
Fairchild. We can see that RDS is given when there are two different voltages from gate to source.
I'm gonna look at which
At
one I'm
10
gonna
volts,
use.
the on resistance will be about
See it? So this is for 10 volt, and this is for
27 milliohms. And while at 5 volts, the on resistance is only about 35 milliohms.
alright. And which volt are we
That's
using?
pretty small.
10 volt or 5 volt? Which volt would you say we're gonna use? 10 volt or
And
5
while
volt?
at 5 volts, the on resistance is only about 35 milliamps.
If
Two
I-
different
if I go
voltages
back-
will about
If we go back,
voltage.
we say that the voltage right here, so can be how much voltage.
Since the resistance is between the drain and
So
source,
we can use even 5 volt. Even 5 volt we can use right here, so.
it is known as RDS on and can always be found in the MOSFET's datasheet. For example, this is a FQP30N06L. Let's take a look at its datasheet from Fairchild. We can see that RDS is given when there are two different voltages from gate to source.
Alright, we're gonna examine this a little bit. Look here, so this VGS right here, so you know what this VGS is saying? The voltage between the gate and the source. You see it? So when you use 10 volt, you can get 15 amp of current through the drain. See it? ID right here, so you can get 16 amp of current, and it is typical. Look, you can get 0.27.
But the current consistent in I use the 5 volts.
16. Right. You understand? Right here, so you can use a 5 volt as well, still get 16, and you still can 16 amp can go through the drain. All right. Good morning. Yes. Yes. And but it's typical. You can get 0.35. Right. And the maximum you can get 0.45. Right. But this is the unit of this is in ohms. Alright, unit of this is in ohms. Alright,
At 10 volts, the on resistance will be about 27 milliohms. And
at 5
while
volt-
at 5 volts, the on resistance is only about 35 milliohms. That's pretty small when you think about it. We picked this MOSFET on purpose. It is known as a logic level MOSFET because the voltage from gate to source, VGS, is lower than 5 volts.
you see it? So we can use the 5 volt. So from a specification sheet you can use the 5 volt, and the 5 volt the RDS for the 5 volt is how much again? 0.035, don't it? No, so?
Yeah.
In other words, the threshold to turn the MOSFET on is low enough to be used by an Arduino or Raspberry Pi. Not
Or-
all
or a
MOSFETs
logic
are
gate.
logic level compatible, so it is very important to check to see what the VGS threshold is before using it in your circuit. Since you will probably use a MOSFET in high current applications, it is important to check how hot it is going to get. Here's how we calculate if we need a heatsink or not. The formula to determine
Oh, and by the way, the MOSFET can get very hot. That's why rarely I use it to make amplifier. And then I need to start to experiment again making some amplifier. But I remember I made an amplifier one time, and the amplifier was playing so good, and it started playing louder, until it was burn. As it actually start burn. As I saw that I turned to a little speaker, and it was burn a speaker, burn a speaker coil. It was playing louder. I saw nice until it just burn it up.
and how much power the MOSFET dissipates is resistance times current squared. In this case, the resistance
Is the first to see this formula right here, so? Power is equal to R times I square.
No, that is a
Oh.
regular power formula.
Right, and I usually use I square R. Right? So the R is the RDS.
RDS on,
This RDS right here, so is the resistance between the drain and the source.
and the current is whatever your load will draw. Let's use an example of a motor that draws 1 amp of current. This means we multiply 35 milliohms by 1 amp squared to get 30.
You see the 25 now, 0.035. This comes from the data sheet.
35 milliwatts. Okay, now
So you get 25 milliwatts. Going back to the data sheet again.
we need a few more things from the datasheet. First, we need the junction to ambient coefficient, which is R theta JA, and in this case is 62.5 degrees C per watt. We also need the maximum junction temperature, which in this case is 175 degrees C. Using this formula, we can calculate degrees
Let
C.
me just go back here so a little bit. Look at this right here, so this N channel, this particular one, you can angle 60 volt, 32 amp, and the RDS is 35 milliohms. So this can angle a whole lot of current at 60 volt. Right, so you can put 60 volt between the drain and the source, and that 60 volt can angle up to 32 amp of current, and the resistance between the drain and the source is 25 milliohms. So you can use this information to do the calculation. Right, look at this maximum junction temperature rating, 175 degrees Celsius. And low gauge change and change typical 15 NC, low cross typical 50 picofarad, and the average right here is 100%.
175 degrees C. Using this formula, we can calculate the maximum power the transistor can dissipate without using a heatsink. We take the maximum junction temperature minus the ambient temperature, which is going to be 25 degrees C, and divide by the thermal resistance.
Alright, where do we get this from? The thermal resistance. Data sheet again. Look to see if you see it anywhere. You see it anywhere there, so? Which other data sheet I get from? You get find the other data sheet where they way back here, so. Way up here, so it is. Somewhere it is. It is somewhere there.
That's pretty small when you think about it.
Right,
We
so
picked
it's
this
not
MOSFET
on that data
on
sheet there,
purpose.
though.
It is known
The time going, so we could just say we can. Because
First, we need the
Jauta soon
junction
gone.
to ambient junction temperature,
Since Jauta soon gone, we
which is
just do
going to
this
be
fast.
25 degrees C, and divide by the thermal resistance. This
So
gives
you get this and this for the data sheet. This is the ambient temperature. When I say ambient temperature, the surrounding temperature that you're operating at, which is basically room temperature. All right. And when you do it,
gives a maximum.
Alright, so we know it's a room temperature. That's why they use ambience temperature. Because room temperature is between 25 or something. That is room temperature.
Room
But
temperature.
that's I think there's a difference. I think there's a difference. That's why they use ambient temperature because their temperature which
Right.
at the environment at that time. That's
Right.
most of the
Yes.
most of the car say Canada was great, can go a lot below. So the temperature of the environment at the time. So I don't think they should they use ambient temperature instead of room temperature.
Them use 20 because what they are saying on an average, most of the time the ambient temperature is 25 degrees Celsius because they are assuming that you are using it indoor.
No, but when I say ambient temperature is not really room temperature, it's the temperature of the environment.
No, it's not really room temperature, but it does assume. You understand?
No, but I say that's why them they use they use the term ambient temperature.
Ambient. That's why they use the term ambient.
You just the temperature
Ambient.
around temperature in the environment.
In the environment.
Like Alaska.
Right. If they are place like Alaska, well, they probably will still use the 25. Why would they use the 25? They are assuming that you are using it indoor, but you can use even minus 25 degrees Celsius, which would
minus 25 degrees Celsius adding.
which this would be a positive.
Yeah.
You understand? Because you put this in bracket and put a negative right here, so You understand? But there's a 25 because they assume that most person will use it indoor, which is about 25 degrees Celsius most of the time.
Okay.
You understand?
Dissipation of 2.4 watts. In our example, we are only dissipating 35 milliwatts, so we're safe to operate without a heat.
So when they do the calculation, they realize that that 25 milliwatt is less than 2.4 watt. Um, what they are saying is that you can operate and the system can operate with this 25 milliwatt safely. But when they do the calculation, they get 2.4 watts, which is greater than the 25 milliwatt. Because 25 milliwatt is less than this that they calculate. So they say they can work it without using a heat sink. All right.
Sink
Let me just go back and quick.
by the thermal resistance. This gives a maximum dissipation of 2.4 watts. In our example, we are only dissipating 35 milliwatts, so we're safe to operate without a heat sink.
Suppose we're using 2 amp. How much would be the milliwatt? Or how much would be the wattage? Yeah, use it. Suppose suppose the motor itself.
70 milliwatt.
Suppose
70 milliwatt.
suppose the motor you was using 10 amp.
You have to square it. So 10 times 10, 100 times 100 times the 35.
100 times is 0.035.
Yeah.
And how much would you get?
Multiply that. 100 times 100 times 0.0335. Just go move 0 them around and just get what 100, move it backwards, you get 0.0 so that get about 35. You go get about 35 watt.
35 watt. So what would that tell you? If when you do that and you take information from the data sheet and you come up with 2.4 watt, what would that tell you that you have to do?
You have to use a heat sink.
You'd have to use a heat sink. Everybody understand that? Everybody understand the concept?
Yeah, man, I understand.
Alright, so you're gonna have to watch the video again to understand it.
Now, you might be wondering, how can the number we calculate be 2.4 watts when the datasheet clearly said 79 watts? And that's a really great point. The 79 watts is if we had the ability to cool the transistor's case to 25 degrees C, which means you have to be using some kind of heatsink. But we're going to cover more on that in a later video. Let's review what you need to know to use a MOSFET as a switch. Number 1, find out which pin is the gate, drain, and source. Number 2, look at the datasheet to determine the threshold voltage, which is going to be shown as VGS or VTH. Find the drain to source resistance or RDS on. Number 4, look at R theta JA and the maximum junction temperature to calculate how hot the MOSFET will get. Visit adohms.com/MOSFET-guide, all lowercase, to download a simple PDF form you can use to calculate these parameters. MOSFETs are cool little devices, but they're also a little bit complex, so we'll cover them in more detail in future videos. Make sure you follow us or subscribe to know when new video tutorials are released. If you visit adohms.com, you can also get show notes for this episode as well as other Adohms videos. If you have any questions about MOSFETs or ideas for future
Alright,
videos,
we're gonna look at
send them
another
our way
one.
and keep watching.
Put a link in the
a future
group.
video.
Yes, yeah, I'm gonna put this link in the group as well. It's supposed to be there already, but I'm gonna look to make certain that it's there. Let me just put
Hi,
it in the
I'm
group.
James, the Bald Engineer. Both of these are transistors. One is a BJT and the other is a MOSFET. Can you tell the difference?
Let's copy this and put this in the thing as well. Right. So I have two of them in the link now. Let me save this one. And gonna give you one more now. And then you can be out of here. Let me just go back for this one, for this last one. And then you can be out of here. Right, so this is one of the experiment that Roger them did. So I'm gonna let you see this
Protecting
one.
critical infrastructure from cyber.
I've seen it.
Hold on, I'm gonna show
Hi
it now,
guys, in this lesson
Hold on.
I will explain the basic
Let me just right, I'm gonna share it now.
structure and working principle. Hi guys, in this lesson I will explain the basic structure and working principle of MOSFETs used in switching, boosting, or power balancing tasks in DC to DC converter circuits, motor driver circuits, and many more power electronic circuits. MOSFETs are the most widely used field effect transistors that offer.
And sometimes persons are working with circuits like this, and they are not certain if they are MOSFET. Right, so especially persons who are not knowledgeable about transistors, they will look at these and think that they are regulators, because regulators look like this as well, and persons might believe that they are BJT. But most of the time for these type of switching circuits, they use MOSFETs, especially for this type of power switching circuits.
Operate with voltage control. We can examine FETs in two groups, as you can see here. We had a lesson in which I explained JFET before. I'll explain.
All right. What are one type of JFET?
Eh? What are one type of JFET?
Yeah, one type of JFET. A depletion type, don't it? What is it? N type, N channel or P channel?
Depletion type.
Uh-huh.
I say N channel.
N channel. All right. What about the MOSFET? How many type of MOSFET you have?
You have depletion and you have a depletion and you have also the two type. You have coming at two type.
All right. Go on. Depletion of which type?
I try remember the other type, but I two type care.
And the E type, the enhancement.
Enhancement type, yeah.
Right. And they can be the both N channel and P channel.
Because it can be an increase and enhance.
Mm-hmm.
That's the voltage you
Explain
have
the
come
MOS-
across.
Yeah.
FET in this trouble. The abbreviation of MOSFET comes from the initials of the metal oxide semiconductor field effect transistor words. You see the shape of a MOSFET transistor on the left and the symbol on the right. MOSFET also has 3 pins. As in JFET, one of them is gate, the other is drain, and the last is source. Pin names are the same in MOSFET as in JFET. Their order is not always like this. Location.
You understand? It depends on the writing that is on it. Sometimes the gate might be in the middle, sometimes the gate might be over this side. So this is just a straightforward thing, but the gate can be anywhere at all, the drain can be anywhere at all, and the source can be anywhere at all.
Abbreviations may vary depending on the model. G, D, and S abbreviations are used for these. In the symbol, the pin naming is like this. We can compare the structure of the MOSFET to a faucet, as in all transistors. We can think of the gate pin, where the trigger is made, as the valve of the faucet, and between the drain to source, where the current passes, as the direction in which the water flows in the faucet. When a trigger voltage is applied between gate and source, a current between drain and source is controlled.
And people usually get confused. I remember Arnold get confused with this, because the drain sound like something coming out and the source coming like something going in. So the person might mistake these two and say the source supposed to be on this side and the drain supposed to be on this side. Right?
and source, a current between drain and source is controlled. MOSFETs are produced in two ways, N-channel and P-channel. In the symbol, the outward arrow on the gate pin is N-channel and the inward one is P-channel.
Alright, look at this now. This one right here is the N-channel, and this is the P-channel. Again, some person believe because the BJT, when the arrow is coming out, is a NPN, they believe that for the N-channel MOSFET, the arrow must be coming out. Right? So if you look how this the arrow is going in toward the gate. So the arrow is pointing toward the gate for the N channel, but for the P channel it is pointing away from the gate. Right? So if you understand that for the NPN transistor the arrow is coming the arrow is pointing away from the base. But for the N channel MOSFET the arrow is pointing toward the gate.
If you remember, it was the opposite in JFET. So, what's the difference between them? The working principle of both is the same. The direction of the controlled current in N-channel MOSFET is from drain to source, while the direction of controlled current in P-channel MOSFET is from source to drain. In other words,
Take that in good. So for the N channel, the positive is always on the drain. For the P channel, the negative is on the drain.
while the positive or plus pole of the voltage source is connected to the drain pin of the MOSFET in N-channel MOSFET, the positive or plus pole of the voltage source is connected to the source pin of the MOSFET in P-channel MOSFET. Let's
Don't pay this no mind. Let me just see if I can get to
Wait!
this.
Did you download Grammarly?
Let's compare MOSFET, BJT, and JFET transistors according to the current they can withstand. While currents close to 1 amp and under 1 amp can be controlled with BJT and JFET transistors, much larger currents can be controlled with MOSFET transistors.
See it now? So you can use smaller current with the BJT, but with the MOSFET you can use greater current. So you can control bigger current, right? Above 1 amp. If my load the BJT we can use above 1 amp as well. But this control more current. The MOSFET control more current.
We can see this by looking at the datasheet of some MOSFET transistors. For example, when we look at the datasheet information of the very widely used IRF Z44 MOSFET, there is information that current can be controlled up to a maximum current of 49 amps.
And we have a lot of those MOSFET at the school here that we use for experiment. Roger them used some of them last year.
You know, so the MOSFET, was just, you know, I said sometimes I feel understand. You know, so it's sometimes I fix UPS. I know that.
And a MOSFET them use.
A MOSFET them use.
Right.
And then each of them have some heat sink pan it, you know, some big heat sink pan.
Right. And before the class finish, I'm gonna show you how to test it with the tester. Use the tester and test it. Roger them do it. Roger and Tracy them did it last year. They test it using the tester and they short it out with their finger. Can you can use a finger to short it out, to short out the gate and the drain, and then you apply a current to it, and you can turn it on. So they use the tester to turn it on. There's a voltage from the tester itself to turn it on, and I realize it works.
This current value is really a great value. In addition, a maximum voltage of 55 volts can be controlled with this MOSFET. When we look at the datasheet of IRF 540 MOSFET, another widely used MOSFET, there is information that a maximum current of 23 amps can be controlled and a maximum voltage of 100 volts can be controlled with it. The fact that a wide range and much greater current and voltage control can be achieved with MOSFET increases the attractiveness.
Look at the RDS on. See it? Less than or equal to 77 milliohms.
Of MOSFET compared to other transistors. For example, you see a DC to DC boost converter here. The circuit diagram for this is basically the same as here. The amplification process is according to the switching speed of the
boost converter. And with a boost converter, you can set up a DC power supply where you get a whole lot of current, DC to DC. So it will increase the DC coming out of the system, right? So you can get a power supply. You can set up a power supply. Let's say, for instance, you have a rectified power supply, like the one that you made already. Then you can set up a boot converter on it by using a MOSFET and put in what is known as a trigger or a duty cycle voltage in it, right? A pulsating DC in it, and you can get a much more current than what the current the power supply that you had built. You can get much more current out of it, out of the power supply, by using a MOSFET. Set it up like this. And sometimes sometimes people might see this boost converter and they might think that it's just a power supply with two regulator or with a regulator in it, and they mistake the FET for a regulator, right? Because the regulator looks the same way, just like this, cheaping, looking like a transistor, looking like a BJT. And for persons who are not knowledgeable of these things, we'll try to replace them with a BJT that looking like this, not looking at the model number, and just look at the shape and you say, alright, maybe a chance that will look like this. And we just put it in it, and you make things worse. You might end up put a regulator on it, or you might end up put a BJT on it, and you make things worse, and finish mash a circuit. I see the circuit blazing, and you're wondering why blazing, because you use a different transistor. You use something that's not supposed to be used.
MOSFET located here. Triggers are made at high frequency values at the kilohertz level. In this way, MOSFET and shock diodes are preferred in order to obtain healthier results instead of using normal silicon diodes in order to respond to high-frequency switching speeds in converter circuits. DC to DC converters and motor drivers using MOSFETs naturally get hot because very high current flows through them. As such, they need coolers. We usually see MOSFETs in circuits as fixed to heat sinks that will dissipate the heat, like you see here. For example, in the motor speed control circuit you see on the right here, there is a heat sink fixed to the MOSFET, which I show with the red arrow. We can see that there are heat sinks connected to MOSFETs in this DC to DC boost converter amplifier converter circuit you see on the left. Well, let's look at the basic working principle of a MOSFET now.
And normally,
I don't care what you're doing, you need to stop and listen to this interview.
The only thing we've ever wanted is
go away with that.
Here you see a simple motor.
Alright. Normally now, I would let you do an experiment with this. This is what Rotterdam did. I think they still have some of these circuits here, because I have to put them down for Ttpc to come and look at them. So they have some of these circuits still lying somewhere around in some of the boxes right now. Right? That I let them build on some little breadboard.
Speed control circuit with the circuit diagram in the upper left corner. There is a small DC motor connected to the drain pin of the N-channel MOSFET. There is a DC source to drive this motor. Here, there is a potentiometer connected between the gate and source pins of the MOSFET to provide the voltage to...
Alright, what kind of MOSFET this is? Is it an N-channel or a P-channel MOSFET?
P-channel.
Sure?
P-channel.
Sure it's a P-channel?
No, say it go in, you know, say in a MOSFET, it can be
it's going in. Alright.
Yes.
For the BJT, the NPN is the arrow is pointing nowhere. It is pointing from the base. From the base.
Yeah.
But this one, this is pointing toward the gate. So it's what? It's an N channel.
N channel.
And that's what confused a lot of people. You understand? If it was coming out now, it would have be a P channel opposite to the NPN. You understand? Remember I was saying it earlier?
To trigger the MOSFET. The reason for connecting a resistor between the potentiometer and the MOSFET is that a reverse current in the MOSFETs does not damage the circuit elements connected to the gate pin. Thanks to the resistor here, the intensity of that current is reduced. Thus, the circuit devices connected to the gate pin are not damaged. If we talk...
What value resistor is this right here?
Type of resistor?
What value resistor is this?
Nah, see good. But brown. I don't see, I don't see color good. When I pass it.
Brown, black, orange.
Brown a 1. Be a 0, but black would be 0.
Yeah, orange will be what?
Orange would be 5 or 4.
No, sir.
Orange, you know it? No.
Orange supposed to be 3, don't it? So it is 3-0.
Yeah, 3.
So this is a 10K. You must look at them and remember 10K. If this was a red, it should be a 1K. If this was a brown, it would be a 100. If this was a black, it would be a 10 ohms.
Yeah, so just remember, so the black we are 0, so no count, because you are 0.
Yeah, 0. Yeah, man, it counts right here. But if this was black right here, it wouldn't count. It would be just 10 ohms. If the black was the last one.
No, so that would be this is a 3 and the black here, so that means a 10,000.
Yeah, 10K. Yeah, this is 10K. But suppose this was a red instead of orange. What would it be if it was a red instead of orange? It would be a 1K.
1K.
Suppose this was a brown.
That would be 2.
No, sir. The brown is 1-0, you know.
Brown is 1-0? Yeah, brown is 0. Black is 0 and brown is 1.
Yeah, so it should be a 100 ohms, don't it? Suppose this was a black.
That would be
10 ohms.
Talk about this circuit. Since there is no damage to the potentiometer, this circuit will work smoothly even if there is no resistor. Now, when we change the resistance value of the potentiometer here, a voltage will be applied between the gate and source of the MOSFET. With this voltage, the MOSFET will be triggered and the current coming out of the positive, or plus pole of our power supply, will flow between the drain and source pins of the MOSFET by following the path we have shown with the arrows, and our motor will rotate with this current. As the trigger voltage will change by increasing or decreasing the resistance value of the potentiometer, the drain current will change and the speed of the motor will change according to this current. We can also control the motor by connecting a power supply that provides a constant 5-volt voltage instead of a potentiometer. While the MOSFET is triggered above 5 volts, it is not triggered at the voltage below.
Alright, I'm going to ask you a question now. If you have a power drill, Jauta, and it's a variable drill, and you can, and if you press it a little bit and it turn on a little bit. I press it more, it turn on more. If you press it in more, it go harder. What device do you think that they use to control that?
A variable, the variable something else they use switch. The variable switch, yes.
Yes. Yes, is this. So next time you're working on that, you're working on your drill, and you see your drill stop working, don't show it to and say it now work. Cause this right here, so the potentiometer is what they use. The one that you use to press on the drill is one like this. But don't think say is a push one. It's still a potentiometer. You understand? The more you push it in, you give it less resistance. The more it come out, the more you release it, the more you release it, it has more resistance. The more you press it in, you get less resistance. So less resistance, more current will flow through.
By connecting a power supply that provides a constant 5-volt voltage instead of a potentiometer. While the MOSFET is triggered above 5 volts, it is not triggered at the voltage below. For a better understanding of this motor speed control circuit, I built the circuit on a breadboard. With a 9-volt battery, we can control the speed of a small DC motor with a potentiometer thanks to the MOSFET in this way. As here, the working principle of systems with big electric motor fans is the same. With MOSFET, we can control the speed of a motor not only with a potentiometer, but also with a microcontroller, as here. Since the
right, I can use a computer, because the computer uses a microcontroller, which is no, not a microcontroller, but a microprocessor, which is the CPU, and we do it through the parallel port. Right. We still have a circuit. We still have a few circuits right here that we use. The
resistance value on the gate pin of the MOSFET transistors is very large. There is no current flow. That is, the trigger part and the part connected to the load are isolated from each other. As such, MOSFET can be easily used with a microcontroller such as Arduino. Thanks to the 5-volt square wave received from the PWM signal output of the Arduino, speed control can be done easily. According to the duty value of this signal, that is, by adjusting the expansion and contraction of the signal, we can make the motor rotate fast or slow. Here, the resistor connected to the source pin of the MOSFET provides protection for the reverse current that may come to the Arduino microcontroller. Since MOSFETs are easily affected by static electricity, and due to the resistor used with it, they are generally used as driver modules, not alone in the circuit. Thanks to these modules, MOSFET connections can be made easily in the circuit. Thus, ease of use is also ensured. For example, microcontroller, motor, and power supply connections can be made easily when the MOSFET is not a standalone MOSFET driver circuit module, as is the case here. When we look inside this module, we see the circuit here. The MOSFET driver circuit module is formed by combining the required resistor and MOSFET connections. Thus, the digital signal input, load connection, and power connection to be connected to the microcontroller are gathered on a module to provide ease of use. This is the basic structure and working principle of MOSFET, which is used in power electronic circuits and many other electrical and electronic circuits, friends. I hope it was helpful and you liked it. Hope to see you in our next lesson.
Alright, last thing we're gonna look at fast now is how to test a MOSFET, and then we're done with finish with MOSFET for today, and then next week we'll just take it up again, and then we'll just go to the 555 timer and the up amp. So let us just look at how you test a MOSFET now. I might look at 2 videos for it. Hold on, just share, hold on.
Get terminal and blacklight to source terminal, and it's showing negative.
Hold on, let me just go way back here.
Symbol of N-channel MOSFET here. There are some easy method of.
Let me just bring up this now. Bring back this. Share. Alright. And these people start to have a funny accent, so you have to just listen carefully at the accent, because the accent are very funny. Yeah. This person's accent is funny, so sound.
Hello viewers, welcome to Ttpc. Today we will discuss some easy method of testing MOSFET using a multimeter. Now here I am using for testing IRF 832 and IRF P250N MOSFET, which are both enhancement N-channel MOSFET. I have shown the symbol of N-channel MOSFET here. There are 3 terminals: drain, gate and source. You can
look again. N-channel are going toward the gate. N channel are going toward the gate.
There are three terminals from this figure. From the left side, the terminals are gate, drain and source for this type of MOSFET. Now most often this MOSFET used as a switch. If you apply a positive voltage at gate with respect to source, then current can flow drain to source. So device come in on state mode, and when the gate to source voltage is 0, then no current flow through drain to source, then device come in off state mode. Thus you can use this MOSFET for switching purpose, and the gate is insulated from the drain and source, so it acts like a small capacitor. Now I will test this MOSFET with the help of this multimeter in on state and off state. For that I have to turn on this multimeter, then I have to select the diode testing mode. You can see here I have selected this diode mode.
By the way, did I show you how to test transistor using the multimeter? Nobody never come class, I couldn't get to show nobody how to do that. So you need to come to the class so I can show you. You must come here one time so that I can show you how to use a multimeter to test your FET and to test your bipolar transistors. So that if you are working on any circuit and you are changing any transistors, whether it is FET or regulator or bipolar transistor, you know how to test it so as you don't take out transistors and throw them away when they are good. You don't take out regulator, throw them away when they are good. And you end up buying new stuff you don't really have to buy. Right? And you don't make the wrong diagnosis. So you'll test, you'll learn how to test so that you know whether they are good or bad. So whether they have to throw it or you buy a new one or you retain the ones that are there.
Next I have to identify the terminal of the MOSFET. From this figure you can see the terminals are from the left side gate, drain and source. Next I have to short all the terminal with my finger for a while.
Right, and I'll let them experiment by doing that, by shorting out everything with your finger, and then they turn it on and check and test it and they see that
now
it come on.
I have to connect the black lead of the multimeter with the source terminal and red lead with the drain terminal. I should not get any continuity between source and drain terminal as the MOSFET is in offset.
Alright. That is between the drain and the source. You're not supposed to get anything until you turn on the gate. When you turn on the gate, then the current start to flow. Right now current is not flowing, right, because it is in the off state. Everything is shorts out.
The method of testing MOSFET using a multimeter. Now here I am using for testing IRF 8. So device coming on, use this MOSFET for switch, act like a small. For that I have to turn on this multimeter. Next I have gate, drain and source. I have to short all the terminal with my finger for a while. Now I have to connect the black lead of the multimeter with the source terminal and red lead with the drain terminal. I should not get any continuity between source and drain terminal as the MOSFET is in offset, as no positive voltage applied to gate. Thus we can check the MOSFET in offset.
And how do you think you'll turn it on now? You have to put a positive to the gate, don't it? How do you put a positive to the gate?
Like a DC, put a voltage.
A DC, alright. So we can use the tester right here to do that. The positive as a tester lead.
Now I am going to turn on this MOSFET. For that I will connect this red lead with the gate terminal for a while. As the gate terminal acts as a small capacitor,
you're gonna try it again now.
It will hold the charge and the MOSFET will remain in on state. Now again I have to connect the red terminal with the drain.
There it is. Is it
As
on?
the MOSFET is in on state now.
Mm-hmm.
I am getting the continuity between drain and source terminal.
Right, and person did that last year for their lab, and they said that it worked.
Thus we can check the MOSFET in on state. Now
Oh,
to
oh,
turn
so
off
me
the
tell you,
MOSFET
so
in.
me tell you,
Yeah.
so when I put it on the day of testing, when I
Uh-huh.
put it on the day of testing, you see, the meter also as a pose a DC voltage on the red.
Right,
Yeah.
right.
Again
Cause
as
remember, I know when you're using the tester, is especially when you're testing the resistance, and
When I say that
when you're
calculation,
testing resistance and diode, it's really a voltage come out. You understand? It's really a voltage come out of the lead. As long as you are testing resistors and diodes, can remember, to test a diode, it have to be reverse bias or forward bias, don't it?
yeah,
And
me understand that.
current have to go through it. So where take the
But
current come from? The current come from the meter.
that's so I tell me that so
Uh-huh.
popular,
Uh-huh.
popular. We must go. We must do a level 4 arch.
Mm-hmm.
Yeah, there's this inspector, something inspector, government inspector.
Uh-huh.
He must say something. Me not call him name because through this record still.
Yeah, uh-huh.
And anyway, so me to the man say, so he must say the circuit dead. So I tell you say the circuit not dead because any test resistor, a current have to go through the resistor. If you
Yes.
test, he must say no,
Yes.
no correct.
And the current coming from the meter.
Yes, so I tell you say correct. Me I tell you say actually current so little, but a little bit of current just go
Yes.
through.
Uh-huh. Yes. Mm-hmm.
So I tell him say, he might tell me say every time I isolate the circuit. Yeah, they take out the meter out of it like a test a house.
Uh-huh.
Like, and he must say, if I take out like he might tell us, if I take out take out it off of the source and they
Uh-huh.
test it. And a
Uh-huh.
dead circuit, it's not a dead circuit because still current have to go come through the meter
Current
to
have to
test
go
the
to the
volt,
meter. But but
test the
but but
voltage.
but the current coming from the meter itself.
Yeah, but I tell you, so the current
But
that come from the meter
right,
itself,
right,
but
but a little
he must
bit. But a little
but
bit.
he must say, so I tell him
Uh-huh.
say I tell him say in short that in fact the circuit is not dead because current still have come through the meter and
Um,
him still
when you're saying that it is dead, is talking about probably dead in terms of the actual
AC current.
voltage and current that is putting on it.
No, me know say
You understand?
he must speak in,
Yeah.
but he not look for he might look for the installation part type. But me I tell him
Mm-hmm.
say
But
him look for
technically, voltage and current still go through it from the
yes, so
meter.
me I tell him
Yeah.
say technically in
Mm.
circuit is not dead because current a come from voltage a come from the meter. Me I
Yeah.
tell him say, and him still could understand me I say. I'm not trying to tell him
Why,
say
ya-
him
why,
must say
why you hot up head man? You go way above the man.
no, but me I tell you say
Is that what that?
man. No, but me I tell you say
Just you're
no,
gonna go. Just you're gonna go put the man on the spot, man.
no,
You go set up the man, man. You
no,
make
but
the man look like fool.
but him inspector and he's he have a master in engineering. He have a master, but he have a master's in engineering.
Yeah, but um, a lot of time person don't really think about them little thing they know. Them not them really think. Them not really think sometimes. Sometimes they probably think too far or too big that they can't see little things like this. They can't see little things like this. You understand? Uh-huh.
He bring up, he put up a video like this, and they showed a
Uh-huh.
resistor.
Yeah.
And but guess what?
Mm.
Like you put up a resistor, like you don't have a resistor testing a resistor,
Uh-huh.
and you put up the resistor and show the meter test the meter. So me I tell him say, oh, me I say to him say, oh, the meter would get you for if you not there's some amount of
Yes,
current.
and that is why
connect the drain and
sorry, and that's why when you are doing straight electrical installation, that they teach about instrumentation where they talk about the multiplier in the instrument and the shunt. You want to do the calculation there before the, sh-
That's why I look for it.
the shunt in the meter and the
Yeah,
multiplier in the meter.
yes,
Yeah.
it show me, yes, it show
Mm-hmm.
me kind of picture and the two field and the science field and the installation field
Uh-huh.
before I see the people in installation. They must
Uh-huh.
come because it's like what they have, like this multimeter here,
Yeah.
my classify as multimeter. You
Uh-huh.
know, say, oh, you, you a person who do electronics, and you go
Uh-huh.
saw somebody pass the
Yeah.
instrument. They
Yeah.
call the multimeter instrument, you know. They don't call
Yes.
it multi.
Yes. Instrument. Yeah, instrument. Yeah, measurable instrument. And
So,
when you have person who do courses. You have courses that they are you take and you. And I swear that they call it instrumentation. Strictly instrument they deal with. Strictly instrument. Any electrical, electronic instruments, any instrument at all. It's like when you're going to plane. I say a whole lot of different instruments in a plane. A lot of different analog and digital instruments. You have a course that you have a course that you can study for that as well. The instrumentation.
yeah, but I tell you, them call the
Hmm.
meter, the multimeter in the electrical field out there.
Yeah, they
Then
call
they
it
call it
instrument. Yes, they call it
instrument. So,
instrument. Instrument. They call it. Cause it's
yeah,
an
so no,
instrument. It's an instrument.
it's an instrument. When I say like a
Yeah.
person that use know it as multimeter.
As
Then just some
multimeter,
concept.
as tester. If somebody said, "Where's the instrument?" Them don't know where you attack. But it's
Yeah,
an instrument.
the
You know.
instrument.
Yes. So when you study multimeter, it's really instrumentation you study. All right.
Get terminal with my finger for a while.
So I shall it out back again.
Now again the MOSFET is in off state. You can confirm it by connecting the black lead with the source and red lead with the drain.
So
Then I am getting no
nothing
continuity
until him turn it
between
on
these
now.
two
So you're gonna
terminals.
turn it on now.
So the MOSFET is okay.
That,
Thus we have
Mr.
checked the MOSFET both in
Mr.
on state and off state,
Huh?
and it is okay.
Time,
Now if
you know,
there
by 11
is
o'clock, I
any
believe.
problem with
Go on again.
I said the time passed me by 11 o'clock. I can't go beyond 11 o'clock. I should have an appointment.
Oh, all right. What time is it now? 10:51. All right. Make us see if we can speed up this. Make us see how far we can go with
the
this.
MOSFET, how to check it? First you have to connect the three terminal with your finger.
So no, so the first one good. So we're gonna
The
check
same
this one if this
procedure
one
can
good
be
now.
followed.
We're gonna check
You
if this
connect
one
the
good.
source with the black lead. You have to connect the drain terminal with
Alright.
the red lead.
Right
You
away.
don't get any continuity for a good MOSFET, but as you can see, I'm getting continuity.
Is it? That means say what happened to this MOSFET? It don't good.
There is a problem in
No.
this MOSFET.
You're not supposed to get that
Again,
guy short so see it? That not
I'm
good.
discharging by connecting all the terminal of the MOSFET.
If I'm gone
Then
into
I'm
there,
testing.
him not supposed to get anything, but him get something. And go across, like him turn it on, he getting the same thing.
So this MOSFET is not okay.
Mm-hmm.
Thus, with this method, you can easily identify whether this MOSFET good or bad. If you want to take the test further, we can use this circuit to test a MOSFET.
And this was the circuit that they built. They built this circuit. Even though they tested to the end, and they set up 2 meter like this, a voltmeter and a meter, and they test it like this. They put the ammeter right here, and they put the voltmeter right down here, and they write down everything that they get. They even put on the VGS, which is the threshold voltage, to find out what voltage. After they turn the potentiometer, after a while the RDS break down, and the RDS resistance gets so small that the MOSFET turn on. So as long as it turn on, that voltage that turn it on is known as the threshold voltage.
Here I am using a 10K pot to vary the gate voltage.
So I'm not gonna go behind this because you're not gonna do this
Now, I'm
experiment,
going
but
to
you can try it on your
connect a
own.
9-volt battery meter.
So I think I'm gonna
And
finish it
MOSFET will
right here.
source. Here 40.
Alright.
Turn off this
Because
MOSFET.
you're not gonna do this lab because you
As
get your
I
3 labs
applied.
already, so you're not gonna get another lab. So I just want you to understand how to test the MOSFET and what MOSFET, what are FET and how you test MOSFET. So we look at we look at what is a FET and field effect transistor, and we look at how to test it, and we look at how you use it as a switch to turn on a motor. So we can look at something different. Well, we don't have to go to no more FET. Anything we're gonna do with FET next week is just some simple calculation. We're gonna calculate the pinch off voltage and the threshold voltage and the RDS. That's all we're gonna do, and then we're gonna go into up amp and 555 timer. Alright, so that is it. I'm going to stop the recording right here. Let me just stop.